So howdy, folks. Thank you guys for coming. My name is Scott Maxwell. I'm a Googler. And our guest speaker today is Diego Porqueras. He is the president and CTO of a company named Deezmaker. In 2012, he hosted a Kickstarter for building a 3D printer, the Bukobot, named cleverly after his dog. And it was so successful, it raised almost 4 times the expected funds, and that helped Diego to go on and fund other 3D printers, including this one right here. This is my personal printer, the Bukito printer, and over the course of Diego's talk, you're going to see it make one of these. So Diego is here to talk to us today about the maker revolution and designing and building a 3D printer and where the maker revolution goes from here. Would you join me, please, in welcoming Diego Porqueras?
Thank you. Cool. Hi, guys. How you guys doing? Like I said, I'm Diego. I started Deezmaker. We kind of had the first 3D printer store in the country that we opened in Pasadena in 2012. And yeah, once I did the Kickstarter, that's when I opened the store, and the ball started rolling from there. He invited me. Thank you, Scott, for inviting me. He invited me to show you guys a little of the process and what the 3D printer is made out of, kind of the components, and how I kind of got to design a 3D printer, I guess, and you know, the details from there. So what I was going to do today is kind of just go over the components of the 3D printer, kind of what they do, what's kind of important about them, and how they function, and then go into a little bit of the software stuff. Any software people here? I figured. So we'll try to jump into the software a little bit, and then we could open it up for like Q&A, because I'll give you kind of a crash course of how a 3D printer works, but then I'd like to know what you guys want to know that I can answer more specifically. Sounds good? Great. All right, so let's just jump right in there. How to build a FDM printer. First of all, there's many technologies in 3D printing. It's not just this type. There's powder systems, there's liquid resin systems, there's a paper one, the one that uses paper. There's a bunch of technologies. I focused on this one because it was a very accessible type of 3D printing. It's very affordable, it's easy to get parts, it's not messy. There's no powder, liquids, or anything crazy to deal with, so it's really easy. It's a very good home-based type of machine, or even an office. As you can see, Scott just carries it everywhere with him. So very practical machine. So that's why I really liked it, and it became my ultimate tool to just create stuff. How many of you guys made a 3D print or worked with 3D printers so far? Yeah? Oh, okay, good. Yeah, so when I started in 2012, I'd ask that question. People were like, what is 3D printing? What are you talking about? Finally, it's great that technology catch up, and it's very, very out there. A lot of competition, too. So to start off, there's basically 5 components to a 3D printer. You got the gantry and the frame. Sometimes they're together, but the gantry is what makes everything move in 3D space. The extruder is what kind of spits out the material, basically. This type of 3D printer is, if you simplify it, it's basically a hot glue gun, a very fancy hot glue gun. It just melts material and pours it into layer by layer. And when we get to the software part of things, you'll see how that happens in a little more detail. And then you have the platform, which is where your object starts from. It can't kind of start in outer space, so it has to start somewhere. So in this case, the platform is where everything grows from. And to make all that happen, you have all the electronics that holds everything together. It makes the motors move, the temperatures remain steady, it reads in the data, all that stuff. That's the electronics part. And then the filament, finally the filament is what creates your object and what eventually becomes the object that the machine outputs. Right, so let's jump in there. So first, you have the gantry. And something about what's cool about 3D space is there's many ways to deal with 3D space in a mechanical way. So if you're trying to make a 3D printer, you kind of have to decide the pros and cons of what kind of gantry system you want for what kind of advantages that you want to create for the machine that you want to create. Because they all have their little pros and cons. And there's a few more details about all these that I'm going to talk about. but I'm going to give you kind of the basics of what each gantry system, how it helps, or maybe it's not so good, and vice versa. So first of all, there's pretty much 3 basic sets of how to move in 3D space. You have 3D space is X, Y, and Z, right? So you need usually you move in 2 of those dimensions, and then constantly, basically, as a full layer, a 2-dimensional layer. And then the Z is usually the one that makes it into the 3D part. So your regular paper printer is a 2D machine, right? So it's X and Y machine. But what makes a 3D printer is that it moves up into the Z axis and creates another layer on top of that one. So there's 3 different ways to kind of do that in a 3D printer. Basically, you can move the X and Y, move them in your X and Y direction, and then the Z moves in a certain way. Or you could move, the extruder, which is dispensing the material. That could just stay steady, and you can move the platform in X and Y. Or you could do a combination of those where the extruder just moves into X and then moves up also, but the platform is Y, like this one. And we'll go over those quick examples. So for instance, if you've ever seen machines like this, they're kind of more boxy and stuff. They usually work in the X and Y as the extruder, and then the Z in the platform. So the head basically moves like a plotter. If you guys ever done like drafting with blueprints and stuff, or you're like etch-a-sketch, that's a way of doing it. You move in 2 directions for the extruder, and then the Z platform would move down, or you can move everything up, that whole gantry up. So this is one of probably the best ways to make a 3D printer. It has the most advantages, I think, as far as getting a really good output of your print with a lot less effort. So basically, just moving the head means that you know how heavy that head is all the time, and it never changes the weight. So if you fine-tune your printer, you could figure out the accelerations and the jerkiness that it could take and all that, and it's kind of static. It doesn't change over time. So that way, it'll be very consistent prints, and you could build as big as you want, and it'll stay very consistent. The cons about this is that one of the major cons is that it does make the system a little complex. You have 2 axes running in parallel, and motors are going to be in the same area and things like that. So that's one thing. And sometimes people, the way it's designed is if the head is very heavy, it gets even more complicated to make all the belts really tight and the motor stronger and all that. So instead, what they do is they put the extruder somewhere else and they feed into it. And I'm going to explain about that in a little bit. And that kind of compromises a little bit of the extrusion feature or details, but it just makes things a little more complicated. So you'll see, it gets things worked up in a little different way. The next way to do it is moving your platform X and Y, and then just lifting the head up, like in this case, where the head just stays in one spot as the layer prints, and then the head just moves a little bit, but the platform keeps going. This does make in this format, it makes the 3D printer a little bit maybe cheaper, a little maybe easier, but the drawbacks is that you're moving the 3D printed object that's being printed. So throughout your print, the inertias and the weights start shifting, or starts getting heavier and heavier. And you can't really compensate for that in any really good way. So you have to just make everything nice and solid to begin with, which means you have a little heavier motors or heavier stuff to deal with. And also, it's probably one of the least efficient use of space because the whole platform has to move from one end to the other. So you need those margins to deal with that, right? In the other case, like the other machine, the only margin you have to deal with is the head itself. And if the head's pretty small, then there's not a lot of extra footprints compared to how big your printer prints. Right? And then the other form is like the ones I make, like the Bukito. And the reason we made this one is that we decided that making the axes very independent to each other will make them very robust. But so it keeps the machine very simple. So the Y has its own rail and its own direction, its own motor, and that's it. With the platform, the X moves the head back and forth, and then we created a system to move the the extruder up. And I decided to do this because it was, in this way, I actually created the rails to be also the frame. So it became very, very simplified machine. And it's very, very robust. And one of the features that we like bragging about on this machine is that it could print like in any direction. Because everything's very stiff and light and very sturdy type of machine. The disadvantage about this is that you're kind of moving the platform. The thing is, we're not moving it in 2 dimensions. We're only moving it in 1. So it's just a little easier to deal with, and there's a lot less issues compared to moving in the X and Y direction. Right? Cool. So, so this is a picture of the Bukobot, the first machine, the predecessor to this one. And I talk about a little funny thing that I discovered in designing this machine and researching why other people did certain things. In this case, we did the same system as this, but we had you could see the extruder in the middle, and then the whole Z movement in the Z space moves up parallel to each other. So we have two motors and screws to lift all that up, right, to Z. That makes it a little more complex, but it does make it actually practical. And the first questions we've had when we would, show people the machine is they're like, well, why do you have 2 motors with 2 screws on each side? Why don't you just use 1 motor and tie them together with a belt and do it that way, right? So they're always in sync. So if one gets a little, it won't, one won't go higher than the other by itself. The reason is I actually investigated it, and we ended up finding out that using 2 motors independently but tied together electronically was pretty much the same reliability as doing the belt system, but it actually costs less to do it. And you actually get almost double the power because you have 2 motors lifting it up. So even if you have 2 small motors, they're both doing half the weight. And doing the belt system, you have to have the perfect size belt because it has to be continuous belt. So the tightness has to be there. You have to make the bearings and the pulleys and all that. And it ended up actually costing more to do that than just putting 2 independent motors wired together. So that was like one of the cool early discoveries. I'm like, oh, that's why they do that. So it was very interesting to find stuff like that out. All right. So another gantry system that exists, there's a couple other ones. It's called a Delta machine. I don't know if you guys have seen these type of 3D printers. Basically, they use 3 motors and 3 arms to do all X, Y, and Z axes. And the pros about this is that you have 3 exact arms and 3 exact motors, 3 exact belts, 3 exact everything to do all your X, Y, and Z movements. The cons is that you probably guys like that word, algorithms. This type of machine compared to these are very linear, very static resolution. So if it moves, 1 millimeter here, it takes a certain amount of steps. And if it moves it over here, it takes the exact amount of steps to move that 1 millimeter, no matter where it's at. It's very consistent, very, it's like a ruler. These machines work in arcs. So every arc changes constant resolution. There's never a spot where the resolution is the same throughout the platform. And to make that happen takes some pretty serious algorithm and math and a lot of decimal points. And some of these microcontrollers can't handle that many precision decimal points sometimes. So if you get machines like this, you probably want the best chip possible to run it because you have a lot of resolution and math to deal with. And the other thing is it's a little harder to get these really straight because if something's a little off, it might still work fine, but it's not going to be very accurate because one little thing somewhere is going to be really hard to catch or figure out where it's not straight. Cool. And since you're kind of moving the extruder in every direction, you kind of need the extruder to be pretty light. You can't put it's not you can't, it's once you put like a heavy motor on there, then you have a lot of inertias going back and forth. And that starts affecting your resolution, your reliability. Like if it travels too far and it jerks too much, the steps on a motor might change, and then it's completely out of whack really fast. So it's very sensitive. Yeah, and your speed goes down. Yeah, so as your weight goes up, your speed starts going way down really fast. Cool. And then the other one that's kind of out there that I saw, it's kind of weird, is also, it's called a polar machine. There's only a few out there because it's not really an advantageous way of doing it. But in this way, the head kind of actually moves in the X kind of direction and the Z direction like ours, but the plate moves in a circle. And that must be even more serious algorithms to figure that out. And so I think it's like fun machine to watch how it prints, but when you actually print stuff on it, you'll see, I don't know if you could tell in this one, but it creates like really weird like patterns in your object, just because it's a lot of it to do with the rounding of decimal points in the algorithms. Like you can't do, it's just really hard. And these processors can't do that huge of calculations for that. So that's another way of doing the X, Y, and Z movement. All right. The other newer ones that I saw come up because of 3D printing that are here is called Core XY or HBots. And this one's getting very popular because it has a lot of good advantages. It's a little more complex to design. You have to really do some good serious precision where all the stuff goes. But once you have it, it's a very, very solid type of working. And the way it works is you just have two motors in the back or in the front, depends how you design it. And it works kind of like an Etch-a-Sketch. You guys did Etch-a-Sketch at some point, right? So it's just kind of moving two knobs. And depending on the sequence of how you move them together, it goes in different directions. So if you move just one, it might go diagonal one way. If you move the other, it goes the other way, and vice versa. And that's how the kind of HBot works. The good about this is it gets very efficient to make that compared to like the other, just a normal X and Y with a bunch of belts and rods. This one has a lot less component count to do it. But you need a few components that need to be very nice and solid, like the rails and things. This one's very good for mass production, yeah. So this is an HBot, and the way this works is one is attached to one side and one is attached to the other side of the carriage. And depends on the sequence how they move, it makes all your X and Y movements. On the Core XY, this is the Core XY system. And if you guys like math problems and equations or something down there. But it's actually very simple. And the way it works is when you spin one motor, it actually goes diagonal. And when you spin the other one, it goes the other direction. So when they both spin together, it goes in the X or the Y direction. It depends on which rotation they do. And I have a machine that we offer now that actually uses this system, and it's really nice. And it's very compact the way they do it. And the advantage over Core XY, which is this one, over this one, is that the Core XY is naturally self-aligning. It always wants to kind of keep itself parallel to each one because it has the exact same forces pulling on itself every time it moves. The HBot, unfortunately, when you have maybe one rail is dragging a little bit, it's going to want to bind and get crooked pretty easily. So the adoption of the Core XY is a lot better because it's kind of like a self-aligning. You don't have to go and double check that things are straight again if something gets out of whack. It kind of self-does it on its own. So that's something really cool about the Core XY system.
Are there IP issues there?
Huh?
Are there IP issues there?
No, not that I know of, especially because a lot of manufacturers are using it. So if there is, nobody has called it out anywhere. But I think somebody posted this a long time ago. Maybe Leonardo da Vinci. I don't know. It could be way back then. But it came out and it got published, and they talked about it. It's probably some university or something. Yeah, and people adopted it. I believe it's open source. Can't totally do that exactly. It's super possible that it could be. Yeah. Yeah, old drafting boards that had the rulers that moved in parallel, they would use stuff like that. that would help you move them, so that you don't have to just sit there and hold everything. It would just kind of keep itself straight. They had stuff like that going on with that. And plotters, I think some plotters did things like that too. But this is a machine we offer. It's actually made in Germany. It's called the Craftbot, but this one uses the Core XY. And it was a good chance for me to actually see somebody create it, and I have more than 1,000 hours on this machine, and it works really nice. Super steady, never gets out of whack. Very, very well built. Cool. All right, so now we get to the extruder. So like I explained before, this is kind of a very fancy hot glue gun, and it's pretty simple the way it works. The extruder basically consists, it starts off at the top where the material comes in. It has, usually we have a gear, some kind of gear type of wheel with teeth on it, and that kind of forcefully just bites into the material and feeds it through. And you always have the wheel on the other side to just put the pressure on it. There's some extruders there's like another 20 ways to make an extruder, but this is the most common, because you could have teeth on both sides if you want, things like that, but it gets more complicated. And then from there, it goes down usually a barrel, which has to be cold. And then right at the tip is where your heater and a sensor is to heat up the material at the right temperature for what you're working with. And then it comes out of a lot smaller hole. So that's basically how an extruder works. Does that make sense to everybody?
What's with the thin plastic piece?
The what?
It says thin plastic piece.
Oh, well, whoever illustrated this called it thin plastic. Technically, it might be because the motor pulses very gently, but it's so small it doesn't come out of beads. It comes out like a noodle. So it just comes out in one stream, usually. All right. So the main part of the extruder is kind of this one. It's not the most important because they all have to kind of work together. A 3D printer is one of those machines that if one part doesn't work right, nothing really good comes out of it. Like everything has to work in unison and orchestration for it to work right. But this is kind of like what a hot end looks like. And I think I brought one here somewhere. Jyoti? Oh. Do you have the box with the little extruder samples and stuff? Yeah, could you go? Well, we're bringing some. I'll bring some stuff to pass around so you guys could look it up close. But this is a typical design of an extruder, which has a heater cartridge through the hole, and then the main barrel, and then the nozzle tip. And the nozzle is what creates the resolution of your printer. So if it's a 0.4 millimeter nozzle, that means your bead's going to be at least 0.4 millimeters. It can't be skinnier, so it has to at least come out. It's like pushing toothpaste out of a tube. It only comes out that thick. It won't come out skinnier than that. So you can't get resolution sharper than that. So if you want a higher resolution, you got to get a smaller hole for your nozzle. But the important part about this is that the smaller the hole and the bigger the filament, the more back pressure there is, which means the motor that's driving the filament down into it needs to be a lot stronger when the ratio is really big. So in this case, the 175 millimeter thick filament that you'll see mentioned later also is getting a lot more popular because your back pressure is so much less compared. So if I have a thicker filament that's like 3 millimeter, which is the other common size, compared to a 0.5 millimeter nozzle, and a 175 millimeter nozzle with a 0.5 millimeter nozzle with the same amount, the back pressure is like 6 times different actually, because it's a volume-based type of calculation. So there's advantage and disadvantage of the two, but the 175 is getting more popular because it's an easier way to drive that filament through the nozzle. And so you need a lot less hardware and ends up being a little more reliable and things like that. So the heater block has a cartridge and then a sensor right next to it to kind of, so the processor could figure out what the temperature is going on with it. The other really important part about this is that since you have this really hot thing going on at the tip, that heat's going to travel up throughout the extruder all the way up as time goes by, obviously. So most of these extruders, like this one, has a fan in the front, and that keeps that top part fighting the cold back down into that heating area. And the reason is that, that if the filament starts melting too early, it's going to create lots of friction trying to go down that tube, and plastic expands too, so it's going to like try to shove its way down. So the basic rule about 3D printing with this type is you want like the smallest transition between the cold and the hot. So that way, as soon as it gets warm, it just melts and it's there, and you create the least amount of friction. I'm going to pass a couple of these around if you guys want to check them out. So over here, this is a Bukito extruder that you guys could look at. And you guys know it. You probably took it apart yours. And this is from another company also. You guys could trade. And this is the whole extruder mechanism. So you could see that heat sink there. Everything. So it's important to kind of keep that top part nice and cold. And sometimes I get tech support calls, and they're like, "Hey, my filament keeps jamming. What's going on in this?" And one of the first things I started asking is that fan on that top working? They're like, "No." So that usually means that it gets so hot up there that things are just getting stuck way sooner, and then the motor just can't handle it. And then the next part up is the drive gear. We call it the drive gear because it's kind of a gear and it kind of drives the filament down into it. This is like an old-fashioned one. I'm going to pass one of these around. You guys want to see it? This was like the really homemade 3D printed version of an extruder. Here, I'll pass it this way. And that's one of my first prototypes used this because that was the easiest way. You could 3D print a motor with a big gear, and it created a lot more leverage, and you could drive everything that way. Now they're a lot more compact, like this one. Later, if you guys want to come up and look at it, it has a drive gear here, and you can see what's going on and how it works and everything. As you could see there, it's pretty simple. The motor has the main gear part with the teeth, and then there's an idler pulley that pushes that filament against it with some good pressure from that spring. And so that way it has a good grip on it. And these drive gears, the golden ones that you see there, they're actually brass, but those are the ones we manufacture for this printer. And I specifically went to a manufacturer that makes gears, and I worked with them, and we made these drive gears that are really sharp and dig in really good. And we created like one of the most reliable drive gears out there for 3D printers. All right. And now there's two different ways to extrude this plastic. There's kind of like a remote way of doing it, and then a direct way to do it. And the remote way is called a Bowden extruder, and the direct way is just called direct drive. The Bukito works in a Bowden extruder way. And the advantage of that is that you could put a nice heavy motor or heavier, more complicated stuff away from the actual hot end itself. So you could keep your head or your extruder very light. And having the extruder light makes things move faster, and you could do a lot of better mechanical stuff for that. The disadvantage of that is that you have a hysteresis, which means like a little delay. You have a little bit of a delay every time the extruder motor pushes the filament. There's a little trickle compression going on, and then it comes out. So in software, you have to deal with a little bit more fine-tuning of, it should start extruding right before it needs to extrude, and then retract a little before it needs to retract, because there's a little delay between the extrusion here and there. And the other disadvantage is that you can't run flexible filaments very elastic filaments. There's some filaments that are very rubbery, and if you try to push them through a tube, they're just going to kind of create a lot of friction and expand and bunch up and just get stuck there, and it just won't come out of the other end. So a direct drive means the extruder is right next to the nozzle, kind of like the one you're passing on this side. Like the drive system goes right down into the barrel. And that's the advantage of that is that you could print very flexible filaments because there's really not a lot where it could go or bunch up. It's just going right straight down that hot end. All right. Cool. And then there's machines that have multi-extruders. When we started, I created a dual extruder machine. and found out a lot of technical issues with doing that. It's very difficult. But now they're coming up with different ways of doing it. The more brute force way of doing it is the top one. It's there's just 4 nozzles there, and you have 4 extruder motors driving it and extruding, and you have software dealing with which one should extrude first. The disadvantage about that is that every nozzle in this type of setup has to be exactly in the exact same height. So if one's tightened a little harder than the other, one's going to be higher or lower than the other. And that means if one's printing, another of those nozzles might knock over what you're trying to print, or vice versa. When the other one prints, the other one's going to knock over the other one. And that was a very big challenge. So people start coming up with ones like the other one, which is like one nozzle and they feed 3 filaments through it. The disadvantage about that is that now you can't do different materials, mostly because you only have one heat source and they all have to be the same temperature. And then there's other methods of doing it. This one is pretty new and it's getting popular, but he basically got one extruder and then all lines feeding into that one also. But he created this little board that you could adapt to your current printer, and it just gets a signal and it figures out how to retract one and then feed the other one into it. And it could actually change temperatures every time it does that, because only one filament's going through at a time, but it has a very clever switching mechanism, like firmware, software combination to do that. All right. And then another little important thing about extruders is that there's some materials like PLA that you use, and if you notice here, there's another little fan on the machine here, that some materials like to be cooled down as soon as they come out of the nozzle. And the reason for PLA is that when you cool down, it becomes very hard and stiff immediately, so the next layer could go on it very smoothly and evenly, and they won't affect each other. Some other materials like ABS plastic, which is like Lego plastic, they need to be kept warm, actually. It's complete opposite. They need to be kept warm and hot. If not, the layer on the bottom shrinks so much that the next layer up shrinks a little bit and it starts curling up all the bottom layers under that, and it creates a really bad chain reaction during your print. And then, so the other part of the 3D printer is your platform. That's where everything starts. And this is the tricky part. It depends on what you're trying to print. A lot of materials have different surfaces that it likes to work on. The most common one is to use a heated platform, which is just like a hot plate, but it's and it's made specifically to get pretty hot. For ABS plastic, I'll pass this around. These are some materials. For ABS plastic, you need to keep it very warm. So this is like one of the hot plates that we use. And it likes to stick on a capped-on tape, a polyamide tape, which is like this one. So those kind of go together. And then there's nylon and other materials like PETG that like other materials. This is a nylon plate for nylon to stick on. And actually, I didn't peel this away. But this is another material that we're starting to use now that's very high tech. And it seems to stick to a lot more materials than just one or the other. Cool. So this is kind of an example of some things that are out there to do different materials for them to adhere to the platform. The black one is like a commercially available. It's actually, I think, polycarbonate. And that one likes to stick to PLA and ABS when it's really hot. The blue tape is what we use for 3D with printers for PLA that don't have a heated platform. The blue tape is actually the normal 3M Scotch tape that you use for masking when you paint. For some reason, somebody found out that was the best type of tape that PLA likes to stick to. The funny thing is only the 3M Scotch brand seems to work the best. People have tried other formulas, other brands and stuff, and it just doesn't work as nice. And at one point I met a guy that works at 3M at like a networking thing, and I asked him, like, hey, what do you guys do with the tape that seems to work for this PLA? He's like, well, we have really proprietary chemicals to make that happen, and we're not going to tell you what they are. So the thing you think, oh, well, why would the surface of the blue tape work so well? And what it is that they actually have a special surface for that. So the adhesive of the tape going on top of it in the roll comes off of it without sticking to that surface. You know, it has that perfect type of adhesion where it just works. So you could roll it off the roll without it ripping apart or the adhesive going on the wrong side. And then there's polyamide tape, which is the yellow stuff, which I know JPL people see this all over the place. It's a very high temperature, non-conductive tape that they use for electronics, for things. If you see things covered in like gold tape, it's usually this stuff. It's called Kapton or polyamide tape. And ABS likes to stick to that really well when it's heated. And then there's materials like nylon, which we could pass around later. But nylon likes porous materials. So unfortunately, if you have a printer with Kapton tape, you can't really print nylon on it because nylon doesn't like to stick to shiny stuff. It likes porous stuff. So some people just go and get really cheap wood on it, or that other material that's called linen phenolic that has a very micro pore in it, and nylon likes to stick to it. So every material likes its surface for some reason. And then the other important really part of a platform is how flat it is. I've always had people come up to us and they go, oh, that's a cool printer, but could you make a really big one? I'm like, yeah, that's fine, but where are you going to get a flat piece of metal at the tolerances you want to be that big? And the only really good way to do that is to get one machined, and that gets really expensive fast. So most pieces of metal that you get from the stock, you know, after about 10 inches, they just start, their tolerances just go out the door when you're trying to print, you know, 300 micron layers. From one end to the other, it could be completely warped everywhere, and you almost can't even look at it. And then some people go, well, why don't you put a big piece of glass on it? Well, have you ever measured glass? It's never perfect. Each side is a little thinner and thicker than other places. So there's those challenges that you run into when you design a printer. There's these new methods coming out and getting more sophisticated where there's now printers that actually go in through and sense your whole board with a sensor, with like a metal detector, basically. And it creates its curviness and it compensates all your 3D printing for it. Like that orange machine with all the extruders, the guy that designed that one, his name's Joseph Prussia, and he created a heated bed with special targets on it that you could run your software. Even if your printer's like totally crooked, it'll go and find those dots and it'll create the algorithm and the compensation to just print your object straight as possible, even no matter how crooked your machine is. It's pretty neat. But those are the challenges that you run into in creating a 3D printer. And then the next major component is electronics. And what the electronics basically do in a 3D printer, oh, that G moved. It wasn't there earlier. Should have been on the next line. But the electronics in this case of the lower cost machines, they basically take in instructions and just convert that into movement. So the myth about 3D printers is that 3D printers have no idea they're even in 3D space. They could care less. All they do is get some instructions and move the motors and adjust heating and pulse things, and that's it. So you can't like throw a 3D file at a 3D printer and it knows what to do, unless there's specific software to start to convert all that into movement. So that's what they do. And usually what we use is microcontrollers. Does anybody here like work on Arduinos? Any Arduino people? Yeah, cool. So an Arduino is it's an open source platform that you could program your own electronics. And a lot of these 3D printers started in that way. Because the software was there, somebody wrote these firmwares that had all the math and the algorithm and the settings to work with 3D printers. And then all these boards started coming up. This is one of the boards we use that's more sophisticated, that runs the same way as the old type of boards, but it's all more compact. The cool thing about chips now is that they're getting better and better, and now we're starting to use more ARM chips, which are really fast. Like this board is, I think, 16 megahertz, and it's like a normal like 16-bit board. But now all the ARM chips are like 64-bit or 32, and they're like 100 megahertz. So now they could handle all the crazy precision and floating point numbers and all that stuff a lot easier. And so like the Delta machines take more advantage of that because they have to. This is like believe it or not, it's a simple diagram of what a 3D printer uses on these microcontrollers. And you're all going to get tested at the end of the day about this. No, I'm just kidding. But as you can see, it's pretty straightforward. You have a bunch of chips that drive the motors. So they're special chips that actually handle all the current that the motor needs. And all the chip has to do is tell it to pulse and in what direction, and tell it what direction. Should it go forward or backwards? But you have these little things called drivers that are little mini chips that handle all the high current for the motors. And then you have MOSFETs, which control your heaters, and then there's sensors and SD card reader and end stops, and all these things are all controlled by the microcontroller. And we're getting on time. And then there's a bunch of filaments. So after that, you need materials to print with, right? So these are some of the most popular materials. And you guys could check them out either later. Let me see. Yeah, we'll check them out later, but there's a lot of cool materials out there. And one of the newer ones that they're doing, which is kind of cool, because a lot of people are like, oh, can't you print metal? With this type of printer, you really can't print metal, because to print real metal, you got to melt it at 1,000 degrees or whatever. But they're doing filament with like PLA or ABS that have like metal in it. This is a normal print that I did on a Bukito that has iron in it, so it could be magnetized. So it's magnetic. And it's like, oh, cool. That's something cool. So basically what they do is they just grind up really fine metal powder and then mix it at the good ratio with PLA. So it's not strong like metal, but it could act or look like metal. And then these are some of the materials that have to, that are popular. PLA is the most popular. ABS is kind of getting the second popular, but it's actually going to third. And PETG is a new material that's coming up, which is water bottle plastic type of material. It's very strong. It's a lot easier to print than ABS, so you don't need a crazy heated bed to reach 110 degrees. You only need it to about 80 degrees. And then there's like flexible materials, nylons, and then the wood and metal fills, and you'll see samples of that here. All right. And yeah, so what's important about the filaments is that each one has like its characteristics of how it likes to be printed. So there's different types, obviously, but the settings are important, the temperatures, the speeds, the platform surface is important, depends on what you're doing. Some people are like, oh, I print PLA, and then they put ABS in there, and it falls off, and it's not working. They're like, why isn't it working? Not all materials work the same, and not all materials stick to the same things or act the same way. So that's something to look forward to understand. And then there's the retraction thing. Each material has a certain way of liquefying through the nozzle. And sometimes when you want to move from point to point without extruding, you got to kind of suck in that material and move. And that's where retraction comes in. So if you see prints and you see all these little, like fine little lines and stuff, either it was running too hot or the retraction wasn't set right. There you go. So some of you guys already dealt with 3D printing at some point. Did you guys deal with the software end of it, as far as the slicing end of it, by chance? How many of you have worked with the slicer part of it? How many of you guys know what slicer is? Okay, cool. Well, what the slicer is, and what I did is I did a talk, that's where these slides are from, of open source software, because a lot of the slicer software, which is the software that grabs your 3D file and slices and creates code, is a lot of it's open source, and it's pretty cool stuff. So I talked about that, gave some market stuff. But this is a quick workflow of how 3D printers work, right? You start with a 3D model. Sorry, this is a little fancier than it probably should be. You place it into the software in the position, like how big you want it. If you want more than one, you could fill up your whole platform with 3D objects, basically. And then after that, you set your settings up, and then that creates what's called a G-code. And that's basically all the simple instructions of, hey, heat the temperature up to this, move the extruder from here to here with this much amount of volume, and things like that. And then after that, you get that instructions that it generates, and then you send it to the printer, basically, in either a USB form or a micro SD card in this case, or now they're wireless. Some you could connect directly to your computer and run it that way. So STL models. Anybody here write software or deal with 3D software, 3D space a little bit? Yeah? Cool. I don't know if you guys deal with STL files, but STL files is like the lowest common denominator of 3D printing, I would call it. It's basically when your object is just a bunch of triangles to create your solid model that then the slicer uses to figure out how to slice it up. So it's kind of works, an STL is basically a pure object made of triangles. So there's no curves, there's no other instructions of how actually what the scale is. The computer doesn't know how big it is. It's just a number is a number and a triangle is a triangle. That's how usually STL. So they're kind of very, very simplified. So sometimes you might be in the slicer software and you bring in your object and it's like super tiny. You're like, why is it so small? And basically that means somebody exported it like into the inches realm. And then the software, the slicing, works in millimeters. So it thinks, well, 1 inch was 1 millimeter. So it's like completely reduced. Or vice versa. Sometimes if your software deals with inches and your model's like enormous, that means it dealt with millimeters instead. So that's about STL files. But you guys get this really fast because it's software-based. So let me move forward. So let me actually run software. So Kira is one of the more popular softwares, and I know Scott uses it. So this is kind of what the software looks like. It's pretty simple. It has a bunch of settings. What we do is since it's open source, we say to our customer, go, hey, here's the link for Kira, download it. And then we give them the set of what's called profiles, which are all the settings for your machine. So you kind of just go up and open your profile. In this case, we'll do a shortcut. And we'll figure something out like PLA. And that sets all these settings. And in this software, the first panel is basically most of the settings that you end up kind of changing dynamically according to what part you're printing. Like your layer resolution. Could you guys read that okay? It's kind of small. But basically, the first one is your layer height. And what slicing software does, basically, it grabs your 3D model, chops it up into whatever your layer height you select, into like flat two-dimensional pictures, basically. And then after that, it gets the rest of your settings, like how thick do you want your walls and how thick the top and bottoms are. And it gets those 2D slices and then starts creating a tool path of where the printer should be laying down material and how much material. So if all your settings are perfect, you'll get objects like this. The thing about it is that if one of your settings are a little off, your volume of extrusion can be completely wrong. It can either extrude way too much or not extrude enough. So all these settings are pretty important to make sure they're adjusted to the machine you're using and the material you're using and everything. So that's the software end of things. There's also advanced features, obviously, for fine-tuning the speeds, the accelerations, the temperatures, all that stuff you could fine-tune, the retracting, like we talked about, that you got to retract every time it moves from end to end. Yeah, and then sometimes, like in this one, they actually have a different setting for just the first layer. So if you have a printer that has like blue tape or something, you want a little extra extrusion on that first layer, it'll do that. Because it's very important in 3D printing that your foundation, your first layer, comes out good, or else the rest might not be well. You know, if you build a house and they screw up your foundation cement, your house might not stand up very well. So it's kind of the same concept. And then there's some cool software features that some of these softwares do, and one of them is called spiralized outer contour. And this is a cool feature that came a while back, and now they're making it really neat. What it is if you have a solid model that's solid everywhere and doesn't have any weird spaces, what this setting or feature does is that it'll print you a nice solid base first, but then on the walls, if you could imagine the normal printing, you'd print one layer, then move up, and print the next layer, and then move up. What this spiral feature does is it actually prints continuously as a spiral. So every little segment, it moves up a tiny micron up on the Z. So it just creates an infinite kind of like spiral effect that gives you, I don't know if I have anything printed with that, but it gives you kind of like a vase, because you can only print the outside of that with one thickness, obviously. But it gives you very smooth looking vases with no seams, and the resolution looks a lot sharper too. It's a very interesting thing to do. So basically, mathematically, they grab the layers, and then they split the segments of the layers into the layer height itself. So if you have a 0.3 millimeter layer and you have 500 segments, you divide that by 500 segments, and it makes little by little. Makes cool little, and so your object comes out really neat, and it's a continuous, and it actually prints pretty fast. So the quick way to like use this software is you just get like an STL. You kind of load it up like that. Now, if it comes in sideways, depends on your software. You could always rotate it. So you just kind of rotate it pretty easily, right? And in this case, this type of software slices. You could see the corner up here. It kind of slices really fast. Every time you change a setting, it starts beginning to slice again, so you don't have to wait for it or hit a button. And then it tells you how long it would take and everything. And then you could actually preview what it would kind of look like with all those paths, those what's called tool path, which is where the head moves and where it's going to move and where it's going to go faster and slower and all that. So if you hit layers, you'll see the effect of that. My computer is probably not too fast on this, but actually this is a pretty big part. But if you look down deep, you could start seeing the features of this. Oops, too much. Where did I go? I think I'm totally upside down. Okay, there we go. All right, I'm going to change to a smaller part because this is choking the processor. Let's do demo objects. Game of Thrones is a little too complex. You could see one that's there. Anybody watch Game of Thrones? Yeah, we have the little Game of Thrones chair right there. Don't sit on it because it's very sharp. Let's see. Let's do something simple. Castle, maybe? So a small one. Cool. So this is the castle, I guess, very simple. So it's slicing, and then you could see how the layers would look like. And this is just a preview, and it's kind of just outlining stuff. Now, actually, I asked Scott about this, but I guess Google's not working on any type of 3D software that I know of or anything, but I think you guys should. There's a lot of improvements we could use in this world, in this realm of technology. But as you could see, you could change slicing settings, and you can actually see them happen, which is kind of neat. So in general, this type of 3D printing, you don't want to print 100% solid objects, right? So there's the infill setting, which creates like some kind of grid or a honeycomb. Some softwares have different options for that. And that kind of just fills in a lot of the gaps, so your object's strong, but it's not 100% plastic, and it uses up your whole roll of material. So this is something you could like just change up like that, and it'll reslice it, and then you'll see it happening. See what it looks like. So according to your object, like this was probably a solid object when you got it. Yeah. So it's probably solid, but in this case, what he did is he just said, "Hey, don't put any infill in it," and so you get like a cup or a vase. And then he said, "Don't print the top part either," and you could set all these settings in softwares. Cool. Well, there it is. There's the infill with the change that I made. But I think since we're kind of out of time, let's open it up for any questions, and we could get into that. if you guys like. You guys have any questions? But okay, perfect. I know all you guys are doing important work, so I don't want to hold you guys from their job, but I'll be here as long as you guys need. So, do you guys have any questions that you guys might want to talk about? Or? Yeah, go ahead. Oh, okay, that would be cool.
Thanks for the talk. So what prevents your competitors from copying you, from copying the machine?
Technically nothing. I actually, on this machine and my previous one, I actually made them open source. On this one, I hesitate. I call it open source. I didn't quite publish all the parts on it, but if anybody asked me, I willingly totally give it to them. And mainly I did this to kind of slow down a little bit of people just copying my stuff, because unfortunately China actually made one just like mine. Not as good, obviously, but they copied a lot of the same things, and they made it super cheap, and it's unreliable, and people complain about it, but that's the way it works. But on these machines, I did create, because I started in open source. The first machine I got it's called a Persia Mendel, and it was all open source. And I bought a kit and I built it, and because of that, I learned so much about how to build my machine that I felt like I wanted to, pay it forward, basically. So all my machines, since this one, I've opened. The first machine, I actually published all the files. They're all on our wiki, and they're all there. On this one, I published some things here and there, but if anybody ever asks and they're like, "Hey, could I have your file of what?" I just give them the source files. No problem about that. So unfortunately, there's nothing to stop people from doing it, except the fact that open source doesn't mean you can make money off of it, but that's very expensive to stop, so it's not worth it usually. What I always like to, my philosophy is always, let's innovate, let's put out the product, let's make money to make more innovative products and keep ahead of the curve as much as possible, and just kind of keep going. So that's kind of my philosophy of trying to work. So, because people are gonna copy it no matter what, one way or another, especially stuff that they could just buy off the shelf. They'll measure it and make their own, and that's it. So there's not a lot of stuff you could patent on this also, which goes, a little bit of the history is 3D printing was actually invented in the mid-'80s. And sometimes I start my talks like that, and people are like, "What? Where was it? How come didn't know about it?" And what happened is, in about 8-9 years ago, the main patents for this and some other ones expired, because they were patented around '84, and they made it as long as possible, and it took about 25 years for them to expire. And once they expired, that's where the explosion happened, because those companies that had those patents never took advantage of like the consumer level 3D printing, because they're like, "Oh, we're just going to make $100,000 machines for NASA and JPL and car companies." They all use those, the really super expensive ones. So unfortunately, that's what kind of held this technology back, I think. The great thing is that right when they expired, the Arduino was coming into light. A bunch of software was coming. It was a lot easier because of the internet, all this stuff, and that's what made this even fuel the fire even more, with everybody making their own version of 3D printers. Yes? The what? Oh, sorry.
In regards to the patent,
Yes.
I heard a rumor the curable one is actually starting to go, right?
The
UV curable liquid.
Actually, that was a first patent, so that I think already expired.
So do you think there'll be a larger amount of smaller printers that can do that versus the?
There's already a bunch, yeah. There's a lot. This guy made this $100 version called a Peachy printer. I absolutely don't recommend it unless you're just want to play with something funny. But he actually made this 3D printer that's literally $100 or less, actually. It should cost a lot less. But he made it so you run it off an audio jack from your computer. And I know it sounds weird, but it's clever. It's very clever. And you can actually 3D print something, but you can't print anything serious. It's just so inaccurate, I guess you might call it. But basically, it works with a mirror that, with the audio, I forgot how he did it, but with the audio, he made the mirror move in 2 dimensions. And you shoot a laser there, and you cure the resin, and you put the resin in water that's salty, And so as it cures and you drip more water, it moves the liquid back up. And it was very clever. I got to give them that. But not a recommended 3D printer. But now they have like $1,000, $2,000 printers that are resin based. I have one that's about $3,400, $3,000 machine. And that works with a projector, and it projects underneath where the resin is, and it pops it out of the liquid with a Z axis, basically. So yeah, I think that was one of the first, because right after that one was patented, they patented like this one, like right after, like they're like, and then you had, that's where 3D Systems comes from, and that's where Stratasys comes from. 3D Systems had the SLA, which is the liquid resin 3D printer or patents, and then Stratasys had the FDM printers, and they both kind of developed, and then they started gobbling up companies trying to come up with other patents. And so some have the metal stuff, some have the powder ones, and but you know, as soon as these patents start expiring, like all this competition starts coming up. So you'll know when more patents expire. For instance, there's one patent that one thing that we wanted to do, a lot of people wanted to do, is for ABS printing, we needed a heated chamber for a 3D printer that had to be at like 80 degrees Celsius to print ABS parts really well. And they had a patent on it. It's still, I think it's still there, or it might have expired. But nobody could call their 3D printer with a temperature-controlled heating chamber or something. It was like so like abstract. Like it was just like 3D printer with heated chamber or something. So it was like, how do you fight that? So yeah, there's stuff like that happening. So yeah. So cool. Any other questions? I hope. No? Anything? I didn't talk much about the firmware, I guess, but the firmware is pretty simple. If you mess with Arduinos, okay, go ahead. No, go ahead. So the firmware, the machines I made are Arduino based, which means you could use the Arduino IDE to just hook up to the chip and reprogram it to do whatever you want. There's no lock on it. You can't really read the data off of it. You could capture it as a hex file and save it, but you can't like really reverse engineer it very easily the way it's compiled, which I'm sure if you guys work with software, you know what that entails. But it's all open source, so yeah. What we did is we grabbed the open source software and we tweaked the settings and turned on and off features that we didn't want and wanted. We actually fixed a bug in it. Oh yeah, we could talk about a bug in there. It was a very serious bug too. But yeah, so we did that's all open source. It's all available online, and it's always, you know, open source. It's just constantly changing and improving and getting more features and different stuff. So like now you could grab that same firmware we used like 3-4 years ago, and the new version now has like the Core XY features, the Delta features, all that stuff is in there, and you just turn them on and off as you need them, and then just reprogram your chip. It's pretty simple. Yeah.
Quick question. So the future, where do you see this going? It's been around for 8-10 years, and it's
Well, 3D printing's been around, since the mid-'80s, so it's like 30 years.
right. And you made the case, so that's something useful, so to speak. Is that when I'm going to be able to, I don't know, print a chair or something like that?
Oh, well, technically you could print a chair now. You could print anything now. It's a matter of if you could afford it, or if it's actually practical. That's where things are getting better, obviously. Things are, you know, it's always getting smaller, bigger, faster, cheaper. It's always happening. We're at that really good curve right now, though, that so many people are getting into it. All these new ideas and new approaches are happening. New discoveries are made that are getting this technology really moving forward fast. I can't say we're going to have the Star Trek replicators yet, where you just go up to it and go, hey, I want a cup of coffee, and it makes the cup and pours it with it. That's not there yet, but we're getting there. And I think everybody's aiming for that. But the diversity of 3D printing is just like crazily diverse. You have microscopic 3D printers that they 3D print microscopic things to put into your body to either detect things or fix things. And then you have 3D printers that build buildings. It's like this 3D printing, but it lays down cement. If you could imagine that, there's some really cool stuff. If you look it up, you'll find cool YouTube videos about that. This guy made like this castle in his backyard of cement with a 3D printer. Huh? Oh, really? Well, that's one of the first things we started talking about, because we'd have like people interview us and things, and they go, well, where do you think 3D printer is going? And since we were close to JPL, it was very inspiring to have space programs next to us, because we're in Pasadena. But yeah, we would say, hey, you know, the ultimate 3D printer would be to send one to Mars, use its local resources, and start building our housing for us, because I already have my house designed for it. But but I mean, that's like the super ultimate type of 3D printing, which would be awesome. The other thing is, I think, I mean, I would like, and I'm assuming 3D printer is going to be like next to your microwave at some point, where, hey, I need this part because this thing broke off, and it comes out. You know, it's going to be that easy and that, you know, that simple and that diverse. The material science behind 3D printing is like probably the hardest part of it, is how do you get certain materials to function like, you know, production type of materials. And, you know, if you make metal parts, everybody expects it to be a part like you machined it. It's super strong, super thing. But there's also things you do that are discovered new with 3D printing that you couldn't do before, especially in the space program. I mean, there's complex parts that are so light and so strong that has never been accomplished before, because of the algorithms you could use to figure out exactly where to put supports and strengths and holes and stuff to save material and all that, right?
SpaceX is 3D printing rocket parts.
Yeah, absolutely. But it's not they're not 3D printing because they can. They're 3D printing because they could add certain features to that was never done before. I mean, if you imagine things that have valves and channels and stuff, you could do that now without all in one solid part. That before it'd have to be a bunch of parts. That means you have to add bolts, and then you add unreliability because there's a big split there, or there's things connecting and stuff like that. So now it's just like whoosh, one part, and it's like, you know, a third of the weight and twice as strong. So there's a lot of stuff like that, and they're developing more and more of that too. There's one of the ultimate things. This sounds very impossible to accomplish, but they might accomplish it. You guys know the Hyperloop? You guys heard it? You know what it is, right? That train with the tube. So I have this friend he goes to Crash Space. He used to work at SpaceX, and he's like an expert robotic engineer and stuff. And last time I saw him, he's like, yeah, I'm working at Hyperloop, and they hired me, and they're like, they want to make this big machine that basically 3D prints the tube in place. And I'm like, what? That's like mind-blowing. I mean, imagine the materials, like the cabling, everything. He's like, yeah, they needed to, it has to build a tunnel and 3D print it as it goes. It's like, there's stuff like that being developed, so that's pretty intense. It's pretty serious stuff. And it all needs good software. Yeah. But if anybody wants to I'm going to be open with you guys. If you guys ever touch the software on 3D printing and you want my feedback, like I'll give you serious feedback. I'll tell you what I don't like and stuff like that. And if you have any questions about that, I'm totally open to do that. All right? Because I just want this to move forward. So one day I'll just 3D print my body again and I'll have a new one. So yeah. All right. So yeah, any more questions? Anything else? No?
So-
I hope that was cool.
Cool. So please thank me and
informative.
thank you, our speaker.
Thank you, guys.